Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're going to be considering heterocyclic aromatic compounds. These are cyclic compounds in which the ring atoms are carbon and some other element. That is, carbon has been replaced by either nitrogen, oxygen, sulfur, or some other element. Now, these are aromatic compounds that we're looking at, and we will be examining their aromaticity after we consider their structure and nomenclature. So let's begin. The first molecule I want to consider that is an heterocyclic aromatic is this molecule. Now you'll notice that if I didn't have any double bonds in it, this molecule would be Pyridine. But if we add two pi bonds, we end up with the molecule Pyrrole. Oops, sorry. Let's write that correctly. Pyrrole. Now, similar to Pyrrole is when we have this five-membered ring and we replace it with oxygen. Oxygen has two lone pairs. This is Furan. Yes, the same molecule that in carbohydrates from which we derived the furanose ring system. And we can replace the oxygen in Furan with the sulfur, which also has two lone pairs. If we do this, we get the molecule Thiophene. Thiophene. All right. Next, if we redraw a Pyrrole molecule, so here is Pyrrole, put a lone pair on the nitrogen, but we replace one of the corner carbons with a nitrogen. So we have a C double bond N, like an imine in a ring. We have a molecule referred to as Imidazole. If I do the same thing with Thiophene, put an N here, that N has a lone pair. Thiophene, the sulfur has two lone pairs. This molecule is called Thiazole. Notice the common ending, A-Z-O-L-E, between imidazole and thiazole. Now, one molecule that we've had and we're very familiar with is the Pyridine molecule, where we have a nitrogen here with a lone pair. Pyridine, six-membered ring with a nitrogen. What's interesting is if we take a Pyridine and do the same thing we did with Pyrrole, that is, we take this corner and we put in a nitrogen where we had a lone pair. We have the molecule called Pyrimidine. Okay. Now, we can take molecules of naphthalene that stand out a little more. And if we replace the naphthalene with the nitrogen here, That would be the same as if it was here, here, or here in the alpha position of a naphthalene ring. This is called quinoline. Interestingly, if we do the same naphthalene, but this time we put it in the beta position of the naphthalene ring, here, we make isoquinoline. Isoquinoline. Right. Two more molecules that have fused aromatic rings are when we take a 6-membered ring and we fuse it with a 5-membered ring. If we fuse it with a 5-membered ring, we produce the molecule Indole. And lastly, if we take a pyrimidine, so we put an N here and an N here, right? And we add a 5-membered ring, that is an imidazole. So we have an NH, a lone pair. Let's put in our lone pairs. Gotten a little lazy here, stopped drawing the lone pairs. I'll go back and put in the lone pairs. There we go. This is purine. Important base. Fundonucleotides. Okay. All of these molecules are aromatic and heterocyclic, and you are responsible for both the structures, the number of lone pairs on the molecule, and their names. And spelling is important. Now, I say they're aromatic. Do you recall back to last semester the conditions required for aromaticity? The first condition was that the molecule could get flat and be cyclic. Now, if I do a hybrid orbital number count on any of these heteroatoms, I count the lone pair and the number of atoms bound to it, I get hybrid orbital number 4. And I get sp cubed. And sp cubed is not flat. However, we learned that nitrogen can undergo inversion, and halfway through its inversion process of a chiral center, the inversion process is an sp squared state. Sp squared is trigonal planar. If this could get to sp squared, it would go flat. When there's lone pairs, these atoms could reach a higher energy sp squared state if somehow it could gain energy back. The energy it gains back is from becoming aromatic, which is especially stable. So in principle, it is possible for these molecules to get flat and be cyclic. So rule 1 theoretically could be satisfied if it could get aromatic. Rule 2 says that every atom must have a 2p orbital. That is, it's at least sp squared hybridized. Again, reiterating, nitrogen through its inversion process could achieve sp squared hybridization. In fact, any atom that has a lone pair could put that lone pair in a 2p orbital and go sp squared. It's typically higher energy than sp cubed for hybrid orbital number 4. But if you achieve aromaticity, that might stabilize the system. So again, rule 2 seems possible. The last rule is there must be a Huckel number of electrons. That is, for all of these molecules, we must be able to set 4n plus 2 equal to the number of pi electrons. Now, in order to achieve this, we must be able to determine the number of possible pi electrons. When we do this, when we examine molecules, we have several rules for counting lone pairs. When there are only single bonds to an atom that has a lone pair, such as in the nitrogen of Pyrrole or in the oxygen of Furan, you are allowed to count one lone pair, one of the lone pairs. Why? Well, if I take a look at Furan, and I, in this bottom corner, drew an edge-on view of it, putting in the 2p orbitals. I'll make these ones small. So here's one double bond. Here's the other double bond. Then when I draw the 2p orbital for the oxygen for sp squared, I can put one lone pair in it. That one lone pair can delocalize into the ring. The other lone pair is orthogonal or perpendicular to this plane and cannot be delocalized into the ring. As such, you only can count one of the lone pairs. So our first rule is that when there's only single bonds to the oxygen, you can count one lone pair. If there's a double bond to the heteroatom, such as in imidazole right here, okay? If there's a double bond, you cannot count the lone pair. The reason for that, if I draw this again, is when you draw the 2p orbital here, that 2p orbital on that nitrogen is already used with one electron making the pi bond. So the lone pair is perpendicular to the plane of the ring. That is, that lone pair cannot delocalize into the ring. It's not in the same position to interact with all of these. So the net result is what delocalizes into the ring is just the lone pair off this nitrogen, not the nitrogen that has the double bond. So our two rules for electron counting, so we can apply the 4n plus 2 rule, is that when there's single bonds only to oxygen, we can count one of the lone pairs and only one of the lone pairs. And if there's a double bond to the heteroatom, whether nitrogen or oxygen, we can't count the lone pair. So in the case of Pyrrole, we have 4n plus 2 equals 2, 4 for the pi bonds, and 2 for the lone pair, 6. 4n plus 2 equals 6. 4n equals 4. N equals 1. The Huckel rule works if n is an integer. That is, when n gives an integer, you're aromatic. In all of these cases, if you count one lone pair for atoms that have lone pairs and only single bonds, and you don't count the lone pairs when there's a double bond, you get 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. He has a double bond, so I just count the pi bonds. 2, 4, 6, 2, 4, 6. In this case, I can't count this lone pair because he has a double bond to him. 2, 4, 6, 8, 10. 4n plus 2 equals 10, 4n equals 8, n equals 2. All of these will turn out to be aromatic. All right. Well, let's take a closer look at some of the chemistry and specific chemistry of these examples. Grab certain molecules, and we'll look at some of the interesting features. We're going to begin with pyridine and just start with something we covered in the amine section just a few scribble casts ago, and compare it to the molecule which is not aromatic, Pyridine. So this is Pyridine, and this is Pyridine. Now, the pKb's we gave you, pKb of Pyridine equals 8.75. The pKb of Pyridine equals 2.88. It's much lower, much more basic. Now we know, because we've looked at the structure, this lone pair cannot be counted towards aromaticity because it's perpendicular to the pi bond. So this lone pair is not delocalized into the ring. So there's no aromatic effect on the lone pair. There's no resonance effect on the lone pair. We cannot use that argument to explain why this lone pair is less available for protonation. So how do we rationalize this difference? Well, this nitrogen is sp squared, hybridized. There's one atom here, one atom here, and one lone pair. That's hybrid orbital number 3. This has 3 atoms in lone pair, hybrid orbital number 4. This lone pair is sp cubed. Now, p orbitals are more diffuse than s orbitals, and so more p orbital character means a larger orbital. That is, the electrons extend further out into space. Now, when you hold your electrons closer, you hold more tightly, that's like being more electronegative. By its very nature, an sp squared hybridized atom acts as if it's more electronegative, binding the electrons closer to the nucleus, making them less available for protonation. These electrons are less available for protonation because they're in an sp squared hybridized orbital. They're held closer to the nucleus. And that produces a significant difference in basicity. Now, what about the reactivity of Pyridine? Suppose I take a look at Pyridine and I compare it to the reaction paths followed by another aromatic compound that we've studied, benzene. Now, benzene has this pi cloud of electrons that's very stable. It's aromatic. And essentially what it does is repel incoming nucleophiles because it is negatively charged. It attracts electrophiles. But because the aromatic ring is especially stable, ordinary electrophiles are not powerful enough to disrupt the aromaticity and allow reaction. We have to use stronger electrophiles than normal. If we use these stronger electrophiles, such as nitronium ion, NO2+, or we use Br+ derived from a reaction of Br2 and FeBr3, we can do electrophilic attack on the aromatic ring that results in the loss of hydrogen. We can do electrophilic aromatic substitution. Now, electrophilic aromatic substitution may be the main reaction path of aromatic rings, but we have a problem with pyridine. Pyridine has a nitrogen which is very electronegative. It's delta minus. This puts a delta plus on the ring, meaning much less electron density into the ring. Now, what happened to electrophilic aromatic substitution when we did this in the case of benzene? We could put electronegative groups on benzene. These electronegative groups, NO2 groups, were referred to as powerful deactivators. That is, they deactivated the ring towards electrophilic attack because they withdrew electrons, putting more delta plus. And as you added more and more electron withdrawing NO2 groups, you eventually completely deactivate the ring towards electrophilic attack. And you made the ring susceptible to nucleophilic attack, so that if you threw an H2O and warm water Okay, H2O just warmed it. You could do nucleophilic substitution on an aromatic ring, because although the NO2s deactivated the ring towards electrophilic attack, they activate the ring towards nucleophilic attack. Well, indeed, the nitrogen in pyridine affects the same change. If we have a pyridine ring and we have a bromine on the pyridine, we can hit this with ammonia, which is a powerful nucleophile, and some heat, and we can make two-amino pyridine. So this is called 2-amino pyridine. So pyridine behaves differently than free benzene, but it's certainly understandable why. The presence of the electronegative nitrogen is similar to what we observe as to what happens when you put electron withdrawing groups on an aromatic ring. Now, we want to take a look next at the analogous molecule to pyrrolidine, and that is Pyrrole. And I'm keeping the basicities up for Pyridine and Piperidine because it's interesting to compare them. So what I'm going to do after I've erased this is draw a molecule Pyrrole, examine its pKb, and see if we can rationalize any differences. Remembering that pyridine was less basic because it had its lone pair in an sp² orbital. Now let's take a look at the molecule Pyrrole. Now there is experimental evidence to suggest Pyrrole is really aromatic and that the lone pair is tied into the aromatic ring. One of the strong pieces of evidence is the pKb. You see, the pKb of Pyrrole is approximately equal to 14. Now, this suggests that Pyrrole is even less basic than pyridine. Why would that be the case? Well, if the lone pair is tied up in the aromatic ring, it is especially stable. We can see this nicely if I redraw the 2p orbitals once again, and I'm going to draw it quite large so we got lots of room. So sort of edge on. I'll draw small 2p orbitals for the pi bonds. So here's a 2p pi bond orbital. Here's a 2p pi bond orbital. And now I'm going to draw a larger 2p to show where the lone pair is. If this nitrogen went sp², you could get side-to-side overlap between all these 2p's, where you get the 2 electrons from the 1 pi bond here, the 2 electrons from the 1 pi bond, and you'd get this entire ring, if you like, delocalizing. All these electrons. Now, if this lone pair is delocalized into this aromatic ring, it is definitely not available for protonation. So the fact that the lone pair is aromatic in Pyrrole explains this lower pKb. So if I was to suggest why Pyrrole is less basic than, say, Pyridine, even though Pyridine is sp squared, the lone pair is still available for protonation. It's just how tighter, closer to the nucleus. It's less available than Pyridine, which is sp cubed, because it's closer to the nucleus. But in the case of Pyrrole, the lone pair is tied up in the aromatic ring. And even less available for protonation, because to protonate we would disrupt the aromaticity. Now, we have 6 pi electrons, again, which is a Huckel number. Pyrrole's planar. Each atom has a p orbital. It goes sp squared, even though the hybrid orbital number is 4, because it gets energy back from aromaticity. Because its lone pair is tied up in this aromatic ring, it is not available for protonation, and hence Pyrrole's not basic. Now, Pyrrole is important for another reason, which we want to look at just quickly, and that is, let's redraw a Pyrrole. Pyrrole is important because of the important systems that it can make when it links up with itself. And this is referred to as the Porphyrin ring system. Now, the Porphyrin ring system involves 4 Pyrrole rings. 4 Pyrrole rings. I'm not going to put the pi bonds in just yet. All pointing towards each other. So I'm going to draw 4 Pyrrole rings. Here we go. And they're all linked through double bond CH single bond units. So we're going to have and it produces a giant cyclic aromatic system. I'm going to have H's here. We'll start by putting a pi bonds thusly. There we go. There we go. Okay. And there's lone pair here, lone pair here, lone pair here, lone pair here, and of course there's lone pair on the NH groups. This is the basic Porphyrin ring system that is found in very important biomolecules, which are the Heme unit, that unit which attaches to the proteins of the surface of the red blood cell that carries oxygen. Chlorophyll A, which is responsible for sunlight capturing in plants. And Cytochrome C, which is very important in the energy cycle of the animal cell. Let's take a look at some of the structures. Well, in the cytochrome C molecule, I expect you to know the Porphyrin ring, but I only expect you to be able to recognize the cytochrome C, heme, and chlorophyll molecules. There is an iron in the middle, and that interacts, of course, with the ends. And we have different substituents off. For example, off of here we have CH2, CH2, HO2C, And off of here we have the same thing again, CH2, CH2, HO2C. We get CH3 here, CH3 off of this guy. Then we've got this huge side chain which is attached to a protein, CHS, CH2, CH, CO, and I'm going to just put a squiggle here, NH. We have a CH3 here, CH3, and off of here we have an S, CH2, CH, and once again more protein hookups, CO, NH. All right, and I think we've got one more methyl right here. This fragment is the key porphyrin system for the molecule referred to as Cytochrome C. Molecule essential to the energy cycle of a cell. Again, I say this is recognized only. But notice how the porphyrin ring system is utilized. Now, if I modify this molecule just slightly, I, for example, change this to a double bond CH2, and I change this to the same thing, a CH, double bond CH2. So I have CH3, CH2, CH2, CH3, CH3. That looks good. I have changed my cytochrome C into the heme unit of the red blood cell. This is the oxygen-carrying porphyrin system. As it binds to the iron, it changes the electronic nature of iron so that it can reversibly bind oxygen. That is, it can pick up oxygen. Oxygen can bind to iron in oxygen-rich areas. And then the oxygen can be released from the iron in oxygen-deficient areas. Again, recognized only. Okay, if we make some major changes now, for example, we change the middle iron to a magnesium. We turn this CH3 here into a double bond CH2. Put a CH3 off this guy. Go around the ring making a changes. That's CH3. This becomes a CH2, CH3, and ethyl. We have a CH3 here. Here we get something different, quite different. We get a 5-membered ring, which has a double bond O, and then a wedge here, 2A. Pointing up is an ester, CO2, CH3. Here is a rather long unit. We have a CH2, CH2, a lot like this, except it's an ester with a very long carbon chain, C20H39. So very long, large molecular fragment off the end of the ester. This becomes a CH3, off of here. There is nothing. This is the molecule chlorophyll. Chlorophyll. Let's try chlorophyll. Chlorophyll A. Of course, chlorophyll A is very important to the process of photosynthesis. It is amazing that pyrrole is so important. In fact, if we take this cyclic porphyrin ring system and we break it up and link a linear chain of porphyrin ring systems, we have the molecule referred to as bilirubin, found in the blood. Bilirubin is important as an antioxidant. Recent research has established this antioxidant role, and further suggesting the importance of the pyrrole ring system in biological systems. All right, well, there you have it. Heterocyclic aromatics, very important molecules. We've only touched on them, but this represents the end of this section and the end of another Scribblecast. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.